Electricity. Static electricity is an excess of charge, whether it's positive or negative, that builds up on an object. Electrons have a charge of negative 1.6 times 10 to the negative 19th coulombs. Protons have the same charge, but of course it's classified as positive. Now let's take a look at an example of how we would use this type of information. How many electrons are there in 74 nanocoulombs? Now you notice right here, nano is a little n. So another way to look at this is if an electron has a charge of 1.6 times 10 to the negative 19 coulombs, how many of them will we need to make 74 nanocoulombs? Now notice, 74 times 10 to the negative 9th, or 7.4 times 10 to the negative 8th. So we take the number of coulombs, multiply it by the charge per electron, and then here's what we're searching for. If we rearrange our formula, we now have the number of electrons are equal to this value divided by this value, as we see here, and we get the number of electrons to be 4.625 times 10 to the 11th. Let's take a look at another example. If you have 0.071 moles of a substance, and each molecule has a negative 2 charge, how many extra electrons do I have? And how much charge do I have? Well, remember, back in chemistry, we found that there are 6.02 times 10 to the 23rd parts in every molecule. So, 0.71 moles will give us less than 6.02 times 10 to the 23rd, because 0.71 moles is less than 1. So we take our 0.071 moles, multiply it by 6.02 times 10 to the 23rd parts per mole, and we get 4.274 times 10 to the 22nd molecules. Now, if each of those molecules has a negative 2 charge, they have 2 extra electrons in each one. We just multiply by 2, and we get 8.85 times 10 to the 22nd, or 13,677.44 coulombs, which is an awful lot. So let's do another example. If the substance was oxygen gas, so we go back up, we have the same information, except this substance is actually oxygen gas, how many electrons would we have in total? So we take the total from 0.71 moles of oxygen, and then add to that the extra molecules that we have from the element itself. So we have 4.274 times 10 to the 22nd. And then, that's how many molecules we have. Then we have 32 electrons for every O2 molecule. That gives us 1.3 times 10 to the 24th electrons, and then we add in our extra right here, and we end up with our final answer. Charged particles create an electric field and therefore apply forces that are similar to forces that you find in magnets. They're not identical, but they're related. If you bring a north and a south magnet together, they will end up being attracted because they're opposites. If you bring north to north, they repel. If you bring south to south, they repel. Electric fields are no different. If you have positives, they repel positives, negatives repel negatives, and positives are attracted to positives. So we use Coulomb's law to describe the forces that are involved. So Coulomb's law is listed here on the left of your screen. The force is equal to K Q1 times Q2 over R squared. K is a constant, 9 times 10 to the 9th newton meter squared per coulomb squared. Q is one charge, usually in coulombs. Q2 is a second charge, also the unit is coulombs. And R is the distance in meters. So let's take a look at an example. What's the force between 5.2 microcoulombs and a 1.2 picocoulomb charge that is 4 centimeters apart? So we take that, put it into our equation, 9 times 10 to the 9th, 5.2 times 10 to the negative 6, because that's what micro is. 1.2 times 10 to the negative 9th, that's picocoulombs, and 0.04 centimeters need to be converted to meters, and then we square that. When we're finished, we get a force of 0.351 newtons. Let's take another example. Assume that there are three charged objects in a straight line as shown here. Find the force on the center objects. So let's take a look. We're going to take a look at Q1. And Q1 right here is going to be pulled in to the left by Q2 because they're opposite charges. So they're going to attract. It's also going to be pulled to the right by this because opposites attract. Now, when you take a look at this line, these numbers here are not as big as these numbers. So the assumption is because the distances, this is shorter and larger, that you're going to end up pulling to the right. And if we take a look at our force diagram, we'll have a force between numbers 1 and 2. That's why they use F12. And force between 1 and 3, F13. F13 looks like it would be larger. And since the first you find the attractive forces between 1 and 2. You do that by using Coulomb's law. Then you do the same thing for 1 and 3. And then since they're in opposite directions, I like to make left negative. And we see that the result is to the right. And using that formula, we find the answer to be 5.7 newtons. The electric charges that create the forces described by Coulomb's law also make electric fields. Now, electric fields are shown with these lines. The more lines, the bigger the electric field. In this case, the electric field of this positive and this negative are the same. Notice, though, that the positive, we have the lines pointed out, and the negative, the lines are pointed in. That's a convention that has been accepted by people in physics for a long period of time. Now, the electric field from the positive is pointed outward. The electric field from the negative is pointed inward. And when they interact, they form unique and beautiful designs. Now, you notice positive to negative. We have this line. It has these arrows. It goes like this. And it makes this real pretty design. But if I take two positives, they go out and they repel each other and they never meet. These lines never form this connection when you have this type of arrangement. The magnitude of an electric field is based on how much force is required to push a charge Q through the field. So if you're going to push against or with the field, it's going to require a force. So you take a look at the formula. The electric field is equal to force for every Q value. So note that the units are newtons divided by coulombs. So here's our example. What is the force required to push a 6.1 microcoulomb charge through an E field that is 9.07 newtons per coulomb? Well, you have E equals F over Q. You rearrange it for the force because that's what you're looking for. So it's E times Q. So 9.07 times 6.1 times 10 to the negative 6th, and you find that the force is 5.5 times 10 to the negative 5th newtons.